It's nice to see you all today. Yesterday we began what are called limits, and that's kind of where I'm going to focus today on. And what I have here, I can just a little bit. What we got here is basically all the things we're going to be looking at graphically, at least, on what is called a limit. So the limit of function is the value of the function that something's trying to become as it, in this case, as it goes to 10. There are three types of limits. The first one is the most important, and it's called an overall limit. So here's an example of a function, y equals f of x. And an overall limit would be like here at 10. You see how there's a little hole. Remember yesterday you did it in Desmos and didn't work perfectly, but there was a hole there, right? Well, you would agree that as x gets closer and closer, so as the x coordinate gets closer and closer to 10, this function is trying to arrive at that hole. And I've decided that that happens to be a height of 4. So the overall limit of this function as x tends to 10 is equal to 4. Now, notice how you write it. You write the limit x arrow 10, whatever the function happens to be called, equals 4. So that's an overall limit. Now, you could, it might seem unusual, but you could actually have a little dot up there. And let's say that dot is at 10. That position, right, that y value of 10 is not the value of the limit. The value of the limit is what the function is trying to become, which is 4. That little guy up there, he's actually the value of the function at 10. So do you see that the value of a function might not match up with the limit of the function as x tends to 10, right? The value of the function at 10 is where that dot is. The limit as x tends to 10 of that function is where this little hole is. So they can and very often are different. Are you okay with that? Overall limit, what the function is trying to be. Now here's two new guys we didn't talk about yesterday, and they're called the left limit and the right limit. Right, this is a piecewise function, and the last thing I remember talking about is that we call this bit the left branch and we call this bit the right branch, but they're broken, right, at 3. And so when we talk about a left limit, we're talking about the limit, right, what the function is trying to be, its limit, as x tends to 3, and you see that tiny little minus above it, 3 minus? That's how we mean left limit. It means you're coming in from the left branch, and would you agree that the function is trying to become 7? So that left limit would be 7. On the other hand, this side here is called the right branch. As you come in from 3 plus, that's how we write down a right limit, you're coming closer and closer and closer. You're trying to become that number. In fact, not only are you trying to become that number, because there's a solid dot there, aren't you that number? And in this case, I'd said it was 2. So what we're going to be looking at for the next few minutes are finding, by looking at pictures of graphs, what the left limit is, what the right limit is, and what the overall limit is. This guy has an overall limit, but won't his left and right limit also be the same number? You know, if you come in from the left-hand side, you're trying to do that. If you come in from the right-hand side, you're still trying to do that. This guy here has a left limit of 7, right, and a right limit 2, but it doesn't have an overall limit. Would you agree this function's not trying to become one number, right? So if you have a left limit and a right limit, which we have here, but those are not the same number, right? They're not the same place, then you will never have an overall limit. On the other hand, if these two are the same, as they are here, you will have an overall limit. So can you imagine a piecewise function where the two pieces come together? If the two pieces come together, you've got an overall limit. If they stay separated, then you're going to have a left and you're going to have a right, but you're not going to have an overall because they don't meet. That makes sense? Right. That's pretty much the concept. So I'm going to zoom over, shoot over, whatever the phrase is, and we're going to look at some questions where you're given graphs. This is from the homework. This is the quickest way for me to do it. And try and make it as big as I can, because there we go. There's a nice little piecewise function. It's got some stuff going on. If I asked you then, what is the overall limit as x tends to 5? You would be looking at this picture and say, okay, as you get closer to 5, the overall limit is there, and I'm assuming that's 2. That seems reasonable. So the limit as x tends to 5 of this function is that value there. It's 2. Okay. What is the left limit as x tends to 2 here? What's the left limit? That's x tends to 2 minus.
3.
Be that one, right? Left limit coming in this way. What is the right limit as x tends to 2? The right limit as x tends to 2.
1.
1. Well, okay. For those who are not so sure yet, here we go. Here's the 2 I'm talking about. If you're doing a right limit, it's a 2 plus. You're coming in on this side, right? You're coming in the right-hand branch, and the answer, the height, is 1. A left limited 2, you're coming in from the left side, and that's 3. What is the value of the function g of 5? What's g of 5 equal to? Not a limit. What's g of 5 equal to? 1. That's it. And that's what all this stuff. And so this is the notation that you use. You see that little 2 plus? Doesn't that mean a right limit? That 2 minus means a left limit. If it just has a 2, that's an overall limit. Okay. And next picture. I'm not even going to call them left and right limits now. I'm going to use the other notation. What is the limit as x tends to 2 minus of f of x? The limit as x tends to 2 minus.
3.
Great. What is the limit x tends to 4?
4.
Yes. What is f of 2?
3.
Okay, see that one? F of 2 is where that dot is. In fact, couldn't that dot be a way up here and that would be the answer? Right, f of 2. Kind of trick question, but here goes. What is the limit as x tends to 2?
Undefined.
Right, and the term that you're going to be, undefined is a good answer, but it's not the one we're going to use. We're going to use DNE for does not exist. Right, so instead of saying undefined, we'll just say does not exist. That way, WebAssign will know what you're talking about. Are we beginning to feel a bit more comfortable about what a left, a right, and an overall limit looks like? Okay. And that one's too similar to the one we've done, isn't it? Ah, good. This one's got a lot going on. So let's try this one. What is the limit as x tends to -3?
4.
4. Let's show it. Right, there's -3, okay? Would you agree that the two pieces are meeting together there, and that has a height of 4? So you're looking for the height, the y value. Okay. The limit as x tends to 0.
DNE.
Yeah, doesn't exist. Okay. Would you agree that at this point the left branch and the right branch are not the same place, right? Does not exist. DNE. What's the limit x tends to 0 minus?
-1.
Oh, sorry, 1. It's
Yeah.
clipped on the left side.
It's on the left side, so it's 1. What is f of 0? It's 1. Okay. Yeah, it's too obvious. Not quite sure what's going on here, but we'll do our best. This curve gets to here, which is what, a height of 3. But on this side, it looks to me like it's got one of those sine functions that goes up and down forever. So that's how I'm going to interpret that picture. So if I said to you the limit x tends to 5 plus, you should tell me the answer was 3. And if I said to you the limit is x tends to 5 minus, I think you should say does not exist. Not obviously what's going on, clear that that's what's going on, but that's how I'm interpreting it. Okay. Limit as x tends to 4. Can I really do that? That's not very easy to read. Let me see if. Oh, okay. Here you do not need to tell me the number. That explains why I can't read them. All you're being asked to do here is say, does it exist? Right, that it is a number, right? So, does the limit as x tends to 4 exist? The limit as x tends to 4.
No.
Great. What about the limit as x tends to 4 minus? Yeah. And limit as x tends to 4 plus? Yeah. If you wanted to know what the answers are, you'd have to guesstimate. The 4 plus, which would be coming in from the right-hand side, would be about 2.2 maybe. And the 4 minus would be about 1.5, 0.5 probably. And that gives me a chance to now return. So hopefully if I gave you a graph similar to the ones we've done, do you feel comfortable you could find the overall limit, a left limit or a right limit if it existed? Right. Feel comfortable about that. And occasionally they'll throw in what is the value of f of 2 or f of 4, right? So we're now going to talk a little bit about the names that we give to certain types of vertical asymptotes. So in 141, we had things called rational functions, where we had things called vertical asymptotes, which is what I'm basically trying to draw right now. Okay, so here is our function y equals f of x. When you look at this function, do you recognize that it has 2 vertical asymptotes? Let's say that's at x equals 7. Let's say that's at x equals 13, right? So there are 2 vertical asymptotes. It's essentially where a function like zooms off to infinity in some way. We're going to look at the limits as x tends to 7 and x tends to 13, and it's going to look very similar to this. There's going to be an overall limit, there's going to be a left limit, and there's going to be a right limit. But now we're looking at how do you describe limits when vertical asymptotes are happening. So first one I'm going to do is the overall limit as x tends to 13 of this function. Right, would you agree that as you get closer and closer to 13, doesn't the answer shoot down vertically? Now you might say undefined, or you might want to say does not exist or something, but actually the answer that we are going to be using is negative infinity. Does that make sense that as you approach 13, the answer goes infinitely negative, right? It goes down the y value. And that is an overall limit, right? Coming in from both sides, off you go. So That's an overall one. Now we also have a right and a left. And a right limit would be coming in from the right branch. So we would write it down as well, let's do it at 7. At 7 plus. And then we do the other one coming in from the left branch. Well, if you did this one, which is the limit as x tends to 7 minus, the answer is positive infinity. And if you did coming in on the right hand side, the answer is negative infinity. Are you okay with the answers are just now versions of infinity? Right. So vertical asymptotes either zoom up to plus or zoom down to minus. We cool? Right. Now we can have a look at, if I asked you for the limit as x tends to 7, right? The overall limit as x tends to 7, what would it be in this picture? What would your answer be?
DNE.
DNE, right? So you see, even in vertical asymptotes, just like in piecewise functions, aren't there going to be some situations where the limit does not exist? Let's move on then. See what that looks like. Your answers in this homework are going to be pretty simple, aren't they? Going to be 4, infinity, minus infinity, and DNEs, right? They're not going to be any solving equations that are going on. Right, okay, so we got a picture with some vertical asymptotes here. What is the overall limit as x tends to -3? Overall limit. Sorry, say again.
Infinity.
Yeah, agreed. What's the limit as x tends to 2?
Does not exist.
Correct. X tends to 2 minus.
Negative infinity.
You're comfortable with this, guys, right? So if you see a picture with some vertical asymptotes, are you comfortable about 2 plus, 2 minus, and the limit is x tends to 2, right? The left, the right, and the overall limit. Oh God, there's a ton here. I'll just do a couple then. What is the limit as x tends to 0? The limit as x tends to 0.
Infinity.
Good. X tends to 6 minus. X tends to 6 minus.
Negative infinity.
I agree. Okay. That's interesting. Okay. Oh. In question 8, you're going to have to sketch a piecewise function. And let's shrink this back. There. This function here is going to be one of these 4 guys. Right, it's either this picture, this one, or this one. And I'll leave you to do that. I can show you it in Desmos maybe tomorrow, but we'll let you play about with it until then. One of these pictures represents this guy, okay? And let's just say for argument, because I don't want to give the show away, let's say it's that one, just for argument's sake. You would click on the picture. That's all you would do. That's your homework. And then it says use the graph, hopefully the correct one, to determine the values of A where x tends to A exists. Right. If you look at this function here, would you agree that the overall limit exists everywhere except at 0? So what you would need to do here is, to answer this question, is you'd need to give me all the values of A where that would be true. So let's show you what that would look like. So I would do a bracket, and I would say negative infinity. Where is infinity? Negative infinity up to 0. Oh, I didn't need that bracket, it did it automatically. And then I would do union 0 to, it was in here, infinity. And there we go. Can you remember doing interval notation, which is essentially what that is from 141. So that's essentially how that's going to happen. Then you've got question 9, where you're going to draw this thing. Hopefully you can figure out which one of the pictures is, and then same kind of question. And now it's talking about this one. This is question 10. Use the graph of this function to state the value of each limit if it exists. So they're interested in, what does this function do as x comes in from the left, comes in from the right, or overall? Yeah, that I think I should show you. So if you hold on for a moment, I'm going to set up Desmos. Here we go. Right, so we're going to go into Desmos, and we're going to sketch that weird function that they just gave us. And so I'm going to go here. I'm going to type y equals x. Hit that little guy there. Put in the square root symbol. And what was it? It is 2 plus x to the power of, and it's negative 2. And there we go. I don't know if you were expecting that, but isn't this essentially a piecewise function? Now, I'm going to zoom in here, because they're only interested in that question, what's happening when x gets closer to 0. Would you agree that this does not have an overall limit? Wouldn't the limit as x tends to 0 plus be 1, and the limit as x tends to 0 minus be negative 1? Do you see how we got all of that just from the graph? And so that's what you were being expected to do. Any questions about that? Or once I've shown you that Desmos does most of it, you know, most of the heavy lifting for you, it's pretty much just look at the picture. So let's close on that one. And okay. There we go. You can't see what I'm doing, but I'm closing and opening windows all over the place, making a right mess of it while I'm doing it. Finally got there. Okay, so here we are. So what we're doing now is still on limits, but pretty much today has all been looking at graphs or making a graph on Desmos and then looking at it. And so I don't think we should expect too much difference, but here is a slightly different take on that question. We are going to draw the sketch of a function that has the following features. The limit as x tends to 1 minus of the function is 4. The limit as x tends to 1 plus of the function is 0. And the value of the function at 1 happens to be 3. And so basically we are going to sketch a function that has these properties. So I would draw an axis. I would choose 1. And then I would say, okay, the left limit is 4. So you're coming in from this side. The answer is going to be 4. The right limit is 0, right? So if you're coming in from the right-hand side, it's going to be 0. Would you agree that fits the information? Left limit 4, right limit 0. And the value of the function at 1 is 3. So I'll put a little dot there. Tell people that's 3. I have just drawn that sketch. Is that the only version that would work? Is there other versions of that same picture? Well, in a way, maybe not major, but there, couldn't you go like this and go like that and have your little dot there? Wouldn't that also work? In fact, aren't there lots of ways to go there and lots of ways to go there? So there is no unique answer. So how does that work in a homework situation? Well, best way to do it is to show you. WebAssign gives you pictures. And so your picture might not be theirs, but you can look at theirs and you can see which one of them match that, can't you? So I'm throwing that one out because you see that dot's at 4 and that dot's at 4. So it's either this one here or it's this one here. So is it the one on the left or is it the one on the right? So we're looking for the one that has that feature, agreed? That one is at the wrong place. This one is at the right place. Boom. So it's a lot easier than you might have expected, right? And that's the end of that. And there's a, you know, a version 13. Here's a version 14. This one here is a video that you watch. And now we're on to the last piece of the puzzle. We've looked at limits on graphs, right? Here's a picture, tell me what the limit is. It could even be infinity. So what's the last piece of the puzzle? Suppose I wanted to know the limit as x tends to 0 of sine x over x. And I could just put it into the calculator, couldn't I, and look at it. I could put it into Desmos and look at it, but I want to do it numerically. And so how does that work? Well, you do a table of values. Now, since I'm interested in the overall limit as x tends to 0, I want the numbers to get closer and closer to 0. So I'm going to start off with negative 0.1 and negative 0.01. And then finally, negative 0.001. And then on the other side, I'm going to be positive 0.01 just for symmetry, 0.01, and finally 0.1. Now you might think that's a lot of work. Why don't I just plug 0 in and get the thing over with? Well, first I'm making sure, and I'm glad I checked, that I'm in radians, because you should always be in radians in calc. And I'm going to do the sine of 0 divided by 0. Would you agree that's what you get if you make it 0? You kind of know what's going to happen, don't you, when I hit this button? But let's do it anyway. Calculus says, I ain't doing it. There's no way I'm going to even try and divide by 0. Bad news. So that's out the window. So I need to get a whole load of values. All right? I need to find out what sine x over x is as you get closer and closer to 0. And the best way to do that is to go y equals on your calculator, type in sine x divided by x, then go second table setup. Okay, second window, second table setup. The only thing you really need to do here is to make sure that guy there on the independent is highlighted as ask. That's all you do. And then leave it. You don't need to keep doing it every time. And lastly, you go second table. Let's delete all that stuff. And I can just go negative 0.1, negative 0.01, negative 0.001, 0.001, 0.01, and finally 0.1. Do you notice in this table that as you merge to the middle, as you get closer to 0, that the answer is essentially at least to 6 decimal places, isn't it 1? And so I can make that assumption. Does that seem reasonable? So if you want to find the limit of an expression and you haven't got a graph and you don't want to try and draw it, or maybe if you try and draw the graph, Desmos doesn't help you in it, you know, you can't tell there's a hole there or whatever. This is a numerical way to do it. And the good news is most of what I did here was done by the calculator. Would you agree I didn't need to do 8 or 6 different separate calculations, right? They're all inside that table, basically ready to be written down. So that's how you should be doing questions such as question 16. Question 17. 18, 19, 20, 21, 22. Okay, so there's a bunch of questions, all basic like that. Do you want to see another one of these table guys, or are you comfortable about how this was done? Do you want to see another one, or are we good? We're good, okay. So let me show you a kind of shorter version of what that's doing. Did you notice that this is overkill? Didn't the answer really come from the 2 guys that are really, really close? And the other ones are just build-ups. I didn't really need to know that. So you can do in quite a few of these questions, and I'm picking one where I could do that. You could do this a lot simpler. So for instance, this is a version of question 21. We're being asked to find the limit as t tends to 0 of 6 to the power of t, take away 1 over t. I can do a very small table. In fact, my very small table is only going to have 2 t's in it. Oops. There we go. Since I'm interested in the overall limit as t tends to 0, don't I need to just pick 2 numbers really close to 0? And I pick 1 on the left and 1 on the right. And I have total control about what those numbers could be. So how about 0.0001 and positive 0.001? That seem reasonable? Now, a couple of things can happen. One of them is that the answer ends up being 6 and 6, or 5.9997 and 6.0003, that kind of thing. But you could make an intelligent guess that the answer is pretty much 6, right? That's the most likely thing now. But it can happen that this answer here is negative 2.999, and this answer here is positive 2.999. Remember that one that we saw earlier where it was in 2 separate places? Remember that function where it was at 1 at the top and -1 at the bottom? Remember that one? Couldn't that also happen here? And if that does happen, then won't you say does not exist is your answer? Okay. Now, I don't need to do any table setups because I don't think there's enough calculations here to make that worthwhile. So I'm just going to do it good old fashioned way. So bracket 6 to the power of negative 0.201. Take away 1, close the brackets, and divide it by negative 0.001. And the answer I got is 1.790. Then I'll do it again with that number. So 6 to the power of 0.001, take away 1, divided by 0.001. And the answer I get is 1.793. Are you happy with maybe a 1.79? You might even be, you know, a gambler and say 1.8. Does that seem reasonable? And there you go. I'm curious. I'm going to tell you what the correct answer to that is. Let's click on it and see. So that was question 21, wasn't it? All right. It takes sort of a day to get there, but oh, ho, 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 ho. Where do you think they got 1.792 from?
The average?
Yeah, I think they took the average. I think they wrote this to 6 decimal places. They wrote this to 6 decimal places and they averaged it out. Or they might have stuck in 4 more zeros here and 4 more zeros here. And both answers look like 1.792, you know, essentially the same number. And if you get a question where it just says, tell me the limit, can't you do this micro table, right? I'm making my name up, right? A little baby table. But you must make sure one number either side, right? In case you get a +4 up here and a -4 down here, that means the answer does not exist. And that can and should be a possible answer. Now, some limits can be infinite. So let me show you one. Let's suppose I want to know the limit as x tends to 3. I'll say that. Now, from your 141 days, you recognize there's going to be a vertical asymptote at 3. So this has got basically 3 answers that could happen. Couldn't the answer be it's plus infinity, it's minus infinity, or it does not exist, right? That's the only 3 answers you're going to get in a story that looks like this, right? And we're going to do it with a table of values. Since I'm interested in 3, can't I just take one of those micro tables? That's my made up name for them. Couldn't I just do that? Would you agree that's 2 numbers darn close to 3? Now, I'm going to get the values of those guys. And again, it's not really worth doing it as a table. It's just plug them in. So I've got 2.99 divided by 2.99, take away 3, close the brackets, squared. And the answer I got here was roughly 29,900, which is a very big number. Now, if I go the other way, I get 3.001 divided by 3.001, subtract 3, and squared. And when I do it this way, I get an even bigger number. So it's a million there. Oh, I only put 1.9 there, but that's fine. I got everything I need to know here. Isn't this going to just get bigger and bigger and bigger and positive? Isn't this just going to get bigger and bigger and positive? Conclusion. It's infinite. Does that seem reasonable? Won't even do the question in detail, but suppose I was interested in the limit at 0, right? And I did this, and this number was negative 75,000, and this number was positive 80,000. If you were being asked to find the overall limit as x tends to 0 of that function, how would you interpret this?
Since it's not given the same number, it just doesn't exist.
If you were trying to visualize it, wouldn't it probably mean the thing looks something like that? Right, on this side it was shooting downwards, and on that side it was shooting upwards. So you get the overall limit doesn't exist, and don't you also get at the same time a little idea of what the thing might look like graphically? Of course, couldn't you get a table where they ask you for 0 minus? Couldn't they just say numerically find that limit? Well, if you wanted to know the 0 minus, wouldn't your table just consist of that guy? Because that's the only guy you're really interested in when you do coming in from the left-hand side. And since it's an extremely big negative number, that would eventually mean negative infinity. I mean, if you wanted to be sure, couldn't you do a negative 0.5 zeros in a 1 just to be absolutely certain? But I think one number typically is enough to convince you if it's okay or not. Have we got any questions so far? Are we good? So we've looked at, here's pictures. Can you tell me left, right, and overall limits from them? Can you tell me, even when it's vertical asymptotes, right, what the left, the right limit might be, or the overall limit? Can you, if I tell you some information in the form of what the limits are equal to, could you do a little sketch of it? You know, like 3 plus was 5 and 3 minus was 7 and so on, that kind of question. And lastly, can you use these numerical techniques and tables of values to predict or estimate what a limit would be, as we've just finished here? That's kind of what we've covered. If you say, yeah, I think I can do all that, then I'm good. Are we good? Then we are finished with that section, which means we can now do how to find limits algebraically, which I like much better. Let's tell you a little bit. Have we got time? Yeah, we've got time for an intro, that's all. If you are being asked to find the overall limit, as say x tends to a of some function, we've already done it graphically. That was today, right? Can't you look at pictures? We've also done it numerically. Wasn't that the table of values, right? That type of method. But now we're going to do it the third and final way. Algebraically, I don't think I spelled it right, but who cares? Here are the methods that you can use to do the algebra version of finding a limit. First method is brute force. Brute force is basically you just plug in the value of x and you get your answer. Seems unlikely. Doesn't happen often, but when it does, it's really good. Give an example of that. I did the limit, or I wanted to find the overall limit as x tends to 3 of x squared plus 1 over x, I could simply just plug in 3 and get the answer, 10/3. Would you agree there's no problem with that because the function doesn't have a problem, right? I mean, if it's just a normal function and you want to find its limit, isn't that the same thing as the value of the function? Now we're doing this a little bit out of order, but that's fine. Our second thing that we're going to be doing, this method is called factor and cancel. And here's an example of it. If I wanted to find the limit as x tends to 3 of this one, you might think that it's got a vertical asymptote at 3, and so your answer could be plus or minus infinity or doesn't exist. And that's very often the case, but not always. In the method called factor and cancel, you factor the numerator and denominator. Do you notice that in this particular case, there's a term that cancels? So what you're now going to do is you're going to find the limit as x tends to 3 of that. So you factor it and cancel. I like the name. And what's that guy equal to? Well, isn't that just brute force? The third one, not going to even show you the technique because we don't have time. It's got a really weird name. It's called the conjugate method. And you will use the conjugate method when I eventually get around to telling you about it, if there's square roots involved in the question. Right, so if you're trying to find the limit of a function and there's square roots anywhere, you're going to use this method called the conjugate. Right, last name for attendance, and bye-bye.
Thank you.
Thank you. Bye.
You're welcome. Bye-bye, guys.
I had a question about the homework for you.
Sure, not a problem. What you got?
So for question 6, I believe, you don't have the same numbers as I do.
I
had a
can
pro-
get the same numbers. Is it in 5-1? Not 5-1, is it in 2-1?
Yes.
Okay, give me a second just to find it. So it's Josh, right?
Yes.
Josh. Gotcha. Okay. Well, it looks like you missed 1 point, so whatever it is, it must be quite minor.
It is very minor.
Okay.
I can't round the number to 6 decimal places, and the question wants it in 6 decimal places. So
Right,
maybe
yeah. So it happened at what, 9.1? Is that correct?
yeah. The like 5, 5 of 6.
Yeah, so it was, so you were close, but not close enough. So I guess your question is, how do I round to the accuracy that they want? So let me write the number down. So they're looking at a 9.1, right? And P happens to be 9 negative 4, and the function is 4 over 8 minus x. And I'm now going to go on the white screen and I'll show you as best I can how I would fix that. Okay. So I need to know Q. Well, at least I got the first guy, right? So you got your calculator and you go 4 divided by, put a bracket around it, and you go 9.1, take away, I did that the wrong way around, sorry. 8, take away x, which is 9.1. There, got it the right way around. And I'm looking at a repeating decimal. So it's negative 3.636363, and I'll do a couple more, 63. So far, so good?
Yes.
Right, so the slope joining the P to Q is the difference in the Y's, difference in the X's. And so I'm going to go this guy, take away that guy. It's a bit messy, but I can do it. Negative 63636363. Take away negative 4 basically adds it. And on the other side, we got 9.1, take away 9. Time for the calculator to take over. Negative 3.6363636363. Add 4. Divided by 0.1. And the answer I get then is 3.63636367. So far, so good.
This is where I didn't get the same answer. For the numerator, I only went to 6 decimal places instead of however many you went to.
Just go more.
Just go
If you
more.
want, if you want an answer to 4 decimal places, do all your intermediary calculations to 5, 6, 7, or 8,
Okay.
and only round off at the end, right, when you've nothing else to do. So in this case, if I rounded off, do you see that 1, 2, 3, 4, 5, 6, I would get 3, 6, 3, 6, 3, 6, 4, and that's actually the answer they're looking for.